So, first of all, we need to find out any unknowns. Your unknowns could come from three sources: translation or displacement in the x direction, in the y direction, or rotations at the nodes. So, nodal rotations. These are your three sources. So, first of all, do we have any translations in the x direction? All the information you need to find the unknowns is by looking at the nodes. So, the nodes tell you all the information for the unknowns. So, at C, we have a roller, and the same at B. In principle, a roller would permit movement in the x direction. You can visualize this. But at A, we have a fixed support, and fixed supports are fixed. They don't allow any rotation, any translations, be it in the x or y direction. So back to our question: do we have any translations in the x direction? C would permit this, so would B, but A would not. So your final answer comes from the fact that we have axially inextensible members. This is told by the question. If you have axially inextensible members. Basically, this means whatever value of load you apply in your structure, you know it's going to deform your shape, but it's not going to change the length of the members. So our length stay the same. So if at A you have a fixed support and B and C would permit translations in the x direction, are you going to have any translations? No, because you have axially inextensible members. So the length stays the same. If the length would not have stayed the same, then maybe this would translate here as B and this one even further, but this is not the case. Next up, translations in the y direction. Once again, here you have a fixed support. Fixed supports do not permit any translations in the x or y direction. They are fixed. At B and C we have rollers. So once again, no, that's not the point of a roller, to permit vertical displacements. It would be the role of a pin. So if you had a pin instead of these, then yes, you would potentially have some displacements in the y direction. So finally, what we need to look at is nodal rotations. So any nodal rotations at A? No, because it's a fixed support. Fixed supports do not permit translations in the x direction, y direction, nodal rotations, or anything at all. Next up, at B, do we have nodal rotations? Yes, we could. We have a roller. So we can write this down as theta B and theta C. We are going to assume the direction is positive, the direction. So assuming clockwise rotation at node B and C means that in our calculation, if we get a positive value of theta, then it's clockwise. But if we get a negative value of theta in our calculation after the slope deflection equations, then it's actually anti-clockwise. So next up, what we need to do is draw the end member moments. So this is your structure. Where are we going to have end member moments? At A, B, C. We're going to have an end member moment called AB. And let's assume, once again, positive. I'll tell you why later. So this is end member moment AB. We also have end member moment BA. So, where's my pen? Once again, clockwise. And end member moment for BA is in equilibrium with AB. I mean, they rotate both in the clockwise direction. Next up, end member moment due to BC. Once again clockwise. End member moment due to CB. Once again clockwise. You're probably thinking, why are they all clockwise? This is once again just an assumption. It gets kind of complicated trying to figure out from these because they kind of contradict each other. So just assume end member moments are positive. And then after our calculations, if you get a negative value for your end member moment at AB, BA, BC, CD, and so CB, and so on, that just means that it's actually acting anti-clockwise. So it's just for reference. Okay, so in purple we have end member moments. What do we have equal and opposite to end member moments? Nodal moments. So let's draw these in this one. Equal and opposite to nodal moment, to end member moments, you have nodal moments acting at the nodes, at the very nodes. So not at the end of the member, because at the end of the member you have end member moments, and at the node you have nodal moments. And the nodal moments are equal and opposite to the end member moments. So like this. CB. Yeah. Okay, next up. We've drawn end member moments, nodal moments. We need to write equilibrium equations. Where are we going to have equilibrium equations? We're going to have equilibrium equations at nodes where we have rotations, like you see. So, let's start at node B. You have moment BA due to member BA, and you also have moment due to BC, and because we want them to be in equilibrium, and you can kind of see they act against each other, they're zero. So equal and opposite, you can see. So hence when you add them up, you get zero, because one is positive, one is negative. Or vice versa, this isn't really correct. So next up, at C, we also have moment CB. Once again equals 0. There's nothing else going on at C. And even at A, you would have some value. Okay. So now we need to write the end member moment equations. So this is the standard form, moment for end member moment A, B, which is fixed, you write as 2EI over the length. 2EI over the length, which is 10. Your value of EI, flexural rigidity, you're given here. But you don't actually need to sub it in. I'll tell you why later. It cancels out at the end. Since we have two rotations theta, which we've confined in terms of EI, and then they just cancel out. So anyway, end member moment is 2EI over length. Then in the bracket, you put 2 theta A plus theta B plus any translations you have in the y direction. That you then divide by 3. But we don't have any in the y direction, like we said earlier. So we can get rid of that. 2 theta A. Do we have any value of theta A? No, because we have a fixed support. So no value of theta A, we get rid of that. Do we have value of theta B? Yes. So you only really have theta B in the brackets. And what else is going on between member AB? On member AB, you have a uniformly distributed load acting. So when you go in the end member moment table, you're going to see that you have a formula. You have lots of formulas. You're looking for the one that looks like this and has a uniformly distributed load. And you see that when you're looking from A towards B, you're going to have minus the UDL times by the length squared over 12. If you are looking from B towards A, which we will do later, you'll see that it's plus. So, in this case, we said minus WL squared. W is 3 kilonewton per meter. The length which we're going to square is 10, and the length, and then we divide by 12 from the table. Next up, moment at BA. Once again, 2EI over length. Your length, once again, is 10. Now, inside the brackets, because we're going from B to A, you would have had 2 theta B plus theta A plus any displacements, none of this. Once again, no value of theta A, so you just have 2 theta B. 2 theta B. One way to remember, if you have 2 theta A or 2 theta B, is, I like to think of it as first you write the theta that has 2. And the theta that has 2 is the theta from the end you're going at. So 2 theta B would be first here, plus theta A. Here you would have, because you're starting from A, 2 theta A plus 1 theta B. But obviously, in this case, the A's cancel out. Okay, now we said earlier from the table you get this value. But now, instead of going from A to B, which was negative, we're going from B to A, which your table is going to say as positive. And then the same values here. 3 times 10 to the power of 12 over 12 to the power of 2. Basically, this just means that your moment, due to the uniformly distributed load, is equal and opposite at both ends. That's all it's saying with the change in sign. So, next up. End member moment due to BC. Once again, 2EI over the length. In this case, our length is also 10 between B and C. 5 plus 5. So, over 10. Now, because we're going from B to C, you'd have 2 theta B and 1 theta C. And like we said, any displacements, none of that. Do we have theta B and theta C's? Yes. So we just write in 2 theta B plus theta C. Between B and C, any external loads? Yes, we have a uniformly distributed load of 10 kilonewtons. So then you go into your table and you look for the one with uniformly distributed load acting at midspan. And you see that you're going to be using minus PL over 4. So you get minus 10 times 5 over 4 because your UDL is 10. Your length is 5. And you're dividing by 4. So that's that. From B to C, negative. Basically from left to right, negative. Then you're going from right to left, and it's going to be positive. Equal and opposite, equilibrium. So that's BC. Now we need CB. 2EI over 10. This time just theta C plus 2 theta B because we're from moment at CB. So you have 2 hold on, let me write that again. So we did BC. Now let's do moment due to CB. You have 2EI over 10 once again, 2 theta C plus theta B because we're starting from C, so 2C, ending at B, so 1B. That's it. Sorry about that. And then plus, because it's opposite of BC, the value due to the point load, 10 times 5 over 4. Okay, these are your slope deflection equations. You also have equilibrium equations. So you can just plug whatever you have here. So MBA plus MBC, you substitute and get 0. Then you rearrange and you're going to find out equations for thetas, theta B and theta C from this one. Next up, you can plug in MCB into the equilibrium equation. And you're going to get an equation for, in terms of theta B and theta B, theta C and theta B. Then you can equate them and find the actual values of theta B and theta C. Once you sub these back in, you get theta B and theta C. Then the value of theta B and theta C that you found, you can sub in to your n-member equations and find the actual slope deflection equations. And then you can draw bending moment diagrams and so on. So that's basically it. And if you get negative values of thetas, just know that the rotation here would not have been positive. It would have been negative, so anti-clockwise. And if you get negative values of n-member moments and slope equations and so on, just know that the assumption here that positive rotation means clockwise rotation means positive number is incorrect. So if you have a negative number for the moment, it means you would have had anti-clockwise rotation. So that's it.